The next one is also, you need the argument of in the complex plane also. Otherwise, you'd be slightly a little bit hand waving. This is a Fourier transform of a Gaussian. Okay, so as it turns out, Gaussian, the Fourier transform of Gaussian is also a Gaussian. So again, because of the symmetry of transform and inverse transform, they are kind of interchangeable, the formula. And this is e to the minus a squared. Okay, and obviously a should be positive because otherwise f would not be a well-behaved function for large t, right? So again, you just keep doing it. So g omega 1/2 pi. Put that in the gram, and now you have the omega t in the same exponential function. Integrate. Okay, the way to do it is do a complete square. So I think we did a complete square before, but let's work that out again. It's quite straightforward. So I mean, there are different way to do it. The way I like to do it is put everything in t. So pull out the coefficient of t squared out. So you have t squared. And for this one, because you have minus a pull out, so you have minus I omega over a times t. But this factor becomes, I mean, this term becomes this one, right? But then you want to add something and subtract something. You add something so that this is the square term. I mean, this is the cos term of a square. I mean, the first thing you multiply by 2 and divide by 2. And this term must be the square of the whatever with the 2, right? So, but now you have to be a little careful. You have an I also. You have to keep the I. So other than the 2, the rest is I omega over 2a. Right, that will make the complete square, right? And then you need to subtract whatever this is. And this is omega square, omega over 2a square, the whole thing square. And with a negative sign because I times I is negative. I square is negative. And negative, positive, so you need to subtract that. Subtract omega over 2a. Okay. No, you add this term, right? You add this term. You
but when you square it, that becomes.
You have squared. I square is -1, but you have a negative sign, right? Negative become positive. Then you subtract it. Okay. And now this becomes a square term, and the rest is a constant. I mean, independent of t, so you can pull that out. E to the minus omega square over 4a square over 2 pi. A square root of 2 pi. I use the different convention. Okay, 2 pi. And now it's e to the minus a e minus I omega over 2a. Right? Because you can now double check that the square of this would be a square term. The cos term is this times that times 2, which is this one. And then the square of the whole thing is this one. Okay. Okay. And now without learning complex variable, you would just kind of hand waving and cause this is just a Gaussian integral. And you just look up your table or something, look up the Gaussian formula for the Gaussian integral and get the, I think, square of pi over a. Remember the Gaussian integral correctly? Anyone remember the Gaussian integral? Yeah, square of pi over a, square root, and then pi over a with inside. Right? And but then with that is slightly handwritten because this is not exactly real. This is there's an imaginary part in the argument. So, but the argument, now that you learn the complex integral, you just need to kind of deform your contour. So this is, if you do an integration, so this is like, you call this the Gaussian C. So this is call this C. This C would be, because D, if you call this C, then dt is just DC because this is just constant. To change dt is just dc, so it doesn't matter, right? But then now this integration is along the path as t is originally real, but then you subtract, you have a negative imaginary part minus I omega over 2a. So you're actually going along this line, along the line with an imaginary part minus I omega over 2a. Right? This is now changed to a z-plane. T is defined as this variable, right? So, but in order that you apply the Gaussian formula, you wanted to integrate along the real axis. So, what you need to argue is that the function has no singularity. If you close the loop this way, this will give you 0. The whole loop, this integral over this loop should give you 0 because this is analytic over inside, right? And then you argue that the integration of the same function along these two lines, which is happening at infinity and minus infinity, z, the real part of z tends to infinity or minus infinity. This two vertical line, the integral along this line would be 0. Okay, and the argument is that this z, this is ac squared e to the minus ac squared. So then work it out there. E to the minus a, you have the real part, right? C squared, you C squared is, right, C is CR plus ICI. C squared is CR squared minus CI squared plus 2I CR squared, right? So we have a, the real part, at least the real part is the CR squared, CI squared, right? And then you have this imaginary part, which is not important because that is oscillatory. This is sinusoidal function. Consider this argument. When you take the CR goes to infinity, so whatever the CI is, CR must be, this is minus. This is minus. CR squared must be much greater than CR squared. So this function, CI squared must, I mean, this, you can ignore the CI squared because CI is always finite over this. In fact, it's just the maximum of this is just whatever this value. But CR it tends to infinity. So the whole argument, because CR squared is infinity, the whole thing goes to 0. The argument goes to 0 at both positive and negative infinity. So this two vertical line is 0. So integrating over this is the same as integrating from minus infinity to infinity because the whole loop is 0. So you can actually say that you can shift the contour from the negative imaginary axis, negative with a negative imaginary part back to the real axis. So this is the same as integrating this, the whole thing, minus AC squared DC along the real axis, and that becomes the Gaussian integral. This is Gaussian square root of pi over a into minus omega square of 4a squared square of 2a. Right, that should be answer. Why didn't I get the 4?
Yeah, shouldn't we multiply the second digit also with that?
Say that again.
Now it's not 0 by 0. You need one more a in the last digit. An a in the.
Ah, yeah, there's an a. Yeah, there's an a. That's why I didn't get it correctly. So cancel it. Right, that is more like it. I forgot this a factor. Yeah. All right, so that is this formula. Okay, and now you can also argue that the inverse transform is the same as this one because the transform, the Fourier transform, inverse transform, symmetric, right? You remember. Now the Fourier transform of that will give you the Gaussian. Also, Fourier transform of Gaussian will give you a Gaussian. Now if you do an inverse Fourier transform, basically inverse transform is also a Gaussian, right? But now this argument is different. So this argument minus 1 over 4a is your new a in the Fourier transform, right? And then the inverse transform should recover this one, right? If you change omega to t, just doing basically the same thing to give you that. You can check what it is. The textbook didn't talk about it. I mean, it should work out. It should work out because 1 over 4a is your a, and then you need to divide it by 2. I mean, it's just you do the inverse Fourier transform. It's basically the following exactly the same. You just basically change I to minus I. So, and then everything goes through, and then this integration will be an integration over omega instead of t, right? And the final version actually is real, so there's no I. So whether you're using I or minus I, it should be the same. So the only thing you need to convert is this e to the minus for I is your I. I mean, for you compare the same thing. So, this the transform should be e to the minus t squared over 4a, right? Just like that. 4a. Now a is this 1 over 4. You cancel with the 4. That is equals e to the minus 18. It's the inverse transform of this. I mean, you have this argument also, square root of 2. Maybe this square root of 2. A is 1/4. And then this is 1/2. It becomes there's a square root of 2a in front. And that is not quite it, right? You see 2 and 2. That is 2a. To a teaspoon. So let's figure out why this is low. This is the Fourier transform. Put the inverse transform. Yeah, you need to multiply it by not just this one. This is this one without this 1/2a. So the inverse transform, you need to multiply extra 1/2a. So you need to multiply the whole thing by 1/2a. The whole thing. Whatever that is, multiply square of 2a, multiplied by inverse of 2a. Okay, so we recover that. Because this whole process, just saying that the Fourier transform of this one gives you this formula, right? When you do the inverse transform, you do the inverse transform of this one, multiply by 1/square of 2a. So you need to multiply by that and copy the same formula by converting 1/4a. Using the formula where a is your 1/4a is your a. Put it here and here. This is here and here. Wait, get back to English. It's just this kind of thing. Sometimes it's tricky, but if you do it carefully, that should work out because there's a symmetry between the Fourier transform and inverse transform. Okay, so that's not too bad.